it's summertime, you should be expecting this sort of thing. Yeah, just not here. Wow. In Michigan, yeah, they're having a camp meeting same time. Yeah, you can expect that twice be hot here. So, that's too bad. Yeah. You live around here in the Pacific? Oh. Yeah, sure. We were just there, Lotus Lake. Yeah. But where are you? Yeah, excellent. Oh, I have so much. This is the problem here. Is I just have fun doing this. Are you serious? Oh, when did you retire? Okay. Wow. That's about when I started getting into it. But yeah. 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 Well, I didn't feel unfair that in my class that we have so many hands-on, interesting things that I feel bad for the other classes. Yeah. Yeah. No, everything's chemistry. Well, I think this is part of our educational system is that I know that there's a lot. We don't have experts teaching in the fields because we're spreading everybody thin, right? So I know we have a lot of biology majors. No offense to biology majors, I make fun of them every time, but they're often end up teaching chemistry classes, and they've had very little training. They may not have been that interested in it, but as part of their job description, and I know a number of situations where that's happening, and they're barely teaching. They're teaching out of the textbook. The only reason I use a textbook is so my students have something tangible that they can go along with. And at least in our department, we don't really need the textbooks for a lot of things. Because we've been there, we've worked in industry, we know a lot of these things already. We've been there, we've done that. We're teaching from our experience. And some of us have more fun doing that than others. But if you don't have the experience, chemistry is really scary, actually. It took me about 10 years to get very comfortable being a chemist and teaching chemistry. So after I started my freshman year in college, but yeah, it takes a while to get comfortable. So I feel bad for those that are just had a couple years in college and then they're okay. Yes. Oh, thank you so much. Thank you for saying that. We need some more scientists to join us. Awesome. Oh, sure. Yeah. Yeah. Oh, awesome. See if I got on my wall. So I used to be in business development. Rule number one was, bring business cards. And since I'm not doing that, I just put a couple in. Yeah, sure. Yeah. So to me, there's always two aspects. You do a spiritual lesson, and you have to let them know it's free. And then here with you guys, it's kind of, no, let's learn the chemistry, let's use the science. Yeah. Fantastic. glad we have him our way. Yeah. No, no. I know he loves the mountains and everything, so. Yeah. Saw the Facebook post. Oh, yeah. Great. Okay, guys, we need to get started. Go off stage. Take your stuff in. Over on the piano back.
Hi. Can we check and make sure that you're working? Because
Oh,
I think they had some issues last
Okay,
night.
test.
Are we off mute?
Unmute.
So let's get it off mute.
It is. Yep.
Yeah.
Sorry, my bad.
All right. Okay.
Okay, thank you.
Good. Thank you.
I thought I checked that. All right. I see 11 o'clock, so I think anything else? Or what's that? Oh, at 2. And they're all set up backstage. Yep. Okay, I see 11 o'clock. I don't know if we're ready to go. I'm just going to assume the guys are ready to go in the back and in the front. And you guys can hear me. Glad you're here. We've got some fun things, again, to do today and to learn. So it's good to be here at camp meeting. Let's go ahead and start with prayer. Father God, I just want to thank you again for each breath that we take and how it's been designed to give us life, to give us power, strength, and it all comes from you. And Lord, beyond that, we need you in our lives to help us see the world around us with your eyes and to see the need in others and to recognize it and to be part of the solution and not part of the problem. So please work with us. Bless our time together as we continue to look in more detail in this amazing world that you've created for us. In Jesus' name I pray. Amen. All right. So yesterday we talked about oxygen, carbon dioxide, and then I was supposed to do nitrogen, totally ran out of time. And so in full disclosure, I actually like to leave nitrogen to the very, very, very end of my talks because then it brings in everything together. And so I'm going to actually try to do it at the end today again, and because we're going to cover some really interesting things that will help underscore the importance of why we have nitrogen in our atmosphere. I think it's the most overlooked molecule. So today we're going to look at the light that's just right, look at the light from our sun, and we'll have a few demos here. And then we're going to discuss how water is trapped on our Earth. It's amazing. And just a huge series of coincidences that have happened to trap water on our Earth. It's not as easy as one would think. So we're going to jump right in it, and we're going to learn about light. I am going to need one of my helpers here. So Carter is going to come up on stage, and we're going to learn how scientists study light. And I have some colored solutions right here. And when we think about light, we also think about how light is absorbed by materials. And I have a very simple mathematical equation on my screen there. The absorption of light is related to, I said simple because it's simple for those who've been using it for a long time, but if you haven't, it may not be. It's equal to this letter E times C concentration times L, the path length. I'm just going to demonstrate what all that means and describe. So if we understand something about the molecule, the concentration, and the path length that the light has to go through, we can understand how light gets absorbed in the parameters we need to think about. All right, so I have my green laser here. Carter, you can go ahead and be my laser guy. And you stand over there and shoot it through, right there on the side, and shoot it and hit the paper. Can you guys see that pretty well, I hope? You see a green light on there? Okay, most of you can see that. That's great. Now, question for the audience here. Which one of these solutions would absorb the green laser light? And I'm going to test it. I heard something. Green. So let's test the green. We'll put that out in front. Now, I want you to notice something before he does that. Doesn't it look different colors between the top part of the flask and the bottom part? They look like they're different. Now, I can assure you it's the same solution all the way through. The difference that your eye can see right away is what's called path length. It's longer path length through the bottom than through the top. It's the same concentration, the same molecule that's in there. All right, Carter, go through the top. If it's being absorbed, we won't see the laser light there. Do you guys see the green laser light going through? Yes, well maybe it's because it's too short of a path length. Carter, go ahead and try through the bottom. Is it going through? Yes, it is. Green does not absorb green light. Aha, so that didn't work. Let's try another color. Okay, well we'll try yellow. Okay, Carter, through the top first. Do you guys see the green coming through? Nice and steady, very good. Now let's go through the bottom. It's still coming through. It looks like it may have absorbed a little bit of the lights, but yellow didn't work very well. Okay, let's try red. Go through the top. Okay, it's still kind of going through, now through the bottom. You guys see any light coming out? He's got it going through. Red stopped the green. It's because this is absorbing green out of the white light spectrum, and actually the colors that are making it to our eye are the red colors. So I have a little cheat sheet here, but what did we learn? We learned that path length, the length that it goes through, is important because it didn't hardly stop it through the top, but it did through the bottom. So concentration and path length make a big difference here. I'll see my clicker real quick, and then we're going to stay here. We're going to try it. So on my slide here, if something's thicker, it can absorb more light, and if it's thinner, it won't absorb nearly as much. So we think about all of these things when we think about absorption of light. Now here's a little cheat sheet for you up on my slide here. So in order to tell what color light will be absorbed, you actually look to see what color the solution is, and this one's red, and then you look on the opposite side of the color wheel, and that's the color it will absorb. So the red one absorbs green. You just look on the opposite side. So I'm gonna, this will be easy one here. We'll start easy. Now go ahead and you do this one. So this is a different lasered light, and we've got red laser light, so I should pick which color to absorb it. Yeah, it looks like orange. I don't have quite orange. What should we try? Let's try yellow here, and then we'll try a couple of others. Okay, through the top, not so much, and through the bottom, I can barely see it. So the yellow is taking it away, but not necessarily all of it, so that's doing pretty good. Let's try the red one. Okay, he's got it right through the top and through the bottom. The light is coming right through. The red didn't do that great a job. Now, let's think about green for a second. How do you make green yellow and blue? So this actually has yellow in it. So let's see if it stops some of that blue. Okay, now put it through the top here. It's pretty bright, and it absorbs it a little bit because it has a little bit of the yellow quality in it. Okay, it's not a true green color. All right. So that's how we can learn about light. Thank you very much. You can go back and sit down for a little bit. Thank you, Carter. Very steady hand there. It's hard to be steady. All right. Okay, so what did we learn? We learned that in order to absorb light, you got to think about how the distance the light is going through something, and what is the concentration. We actually played with the concentrations last night, so it would work out well today. And the thing that I didn't talk about yet is the E. It's called the extinction coefficient. It's how well it extinguishes the light. Because not every molecule absorbs light as well as others. And it may come as no surprise that chlorophyll, that is the chlorophyll molecule that's found in plants, green plants, absorbs very well. And it has a very large E, or extinction coefficient. In fact, it's up there as one of the highest numbers that I know about, and I think as scientists know about. So another one of those amazing coincidences that we find that in plants, they have some of the best absorbing molecules. So the leaf does not need to be very thick because the molecules are awesome at absorbing light. So they absorb red and blue colors, and the green gets reflected back to your eye. That's why they're green. Now, I want to talk about our atmosphere, which has oxygen and nitrogen in these things. Oxygen is terrible at absorbing a lot of different lights. It's just terrible at it. But if you have a lot of it, it can make up for its deficiencies. So scientists know how oxygen and ozone and these molecules absorb mainly ultraviolet light, and we're going to learn about the different types of lights right now. So there isn't just visible lights. That's the light that our eyes work with, the reds through the purple colors.
And that's really a small sliver of what we call the electromagnetic spectrum, or sometimes we'll call it the electromagnetic radiation spectrum. And so there's a whole series of different types of light that I want to describe in essentially chemistry sense. So beyond the rainbow, you can go beyond the red into the infrared, to the microwaves, and into the radio waves. Those are actually very low power parts of the electromagnetic spectrum. They don't do much. Well, you'd say, well, my microwave does a lot of things. It can boil my water. Well, it's actually spinning the molecule around. It's not breaking into the bonds. It doesn't really hurt anything. It can warm them up for sure, and that can be dangerous, no doubt. But when it comes to breaking chemical bonds, microwaves, radio waves, they don't really do that. Neither does the infrared. So those parts of the electromagnetic spectrum are chemically what I would call pretty safe. Now, as we get into the visible part of the spectrum, that's where chlorophyll works, the bonds and the molecules in our eyes and in our skin. It really responds, the chemistry really responds to the visible part of the spectrum. When you get to X-rays and gamma rays, the ultraviolet parts there, those are very chemically unsafe. There's so much energy in that part of the electromagnetic spectrum, it can break bonds. And so this is why X-rays and radiation and these things are very dangerous, because they actually start to fragment the bonds. And if you start to do that in your skin and in your DNA, that can lead to cancer. It can, if it's bad enough and intense enough, it can deteriorate and break apart your skin, and it can be really nasty. And in fact, at least half, if not more, of the deaths that occurred from the nuclear bombs that fell on Nagasaki and Hiroshima in Japan, more than half of them, of the Japanese, died from the radiation exposure that happened from the gamma and the X-rays that came off of the atomic bombs that were dropped. So, and it was even within a few days that it took, because there's so much radiation. It really just, the chemistry just falls apart. Very dangerous part of the electromagnetic spectrum. Well, it may come as no surprise that our sun is finely tuned for this Earth, and our sun is an amazing energy source. And this graph that I'm showing right now shows the type of light that comes from our sun. And most of that is in the visible wavelengths. Now, the sun actually is emitting almost every one of those parts of the electromagnetic spectrum, but it is mainly centered in the visible part of the spectrum. And there's quite a bit of infrared. Between the infrared light and the visible, that's most of the light that's coming off. There's definitely UV light that is pretty intense. There is, and it's hard to see on this particular graph, gamma and X-rays coming off from the sun. So, wow, that's amazing. You'd say, well, that's an amazing coincidence. And, well, it's not that every star makes that kind of light. They're just stars that span the different sizes and the types of light that they can output. You can have blue giants that are emitting mainly in the UV or in the gamma and X-ray part of the electromagnetic spectrum. You can have ones like our sun, or you can have these really large red giants, or just red stars. They can be a variety of sizes that are mainly emitting in the infrared. So they'd be almost invisible to our eyes, these other two, but they would be producing a lot of energy just in different parts of the electromagnetic spectrum. A star does not have to be producing visible light. No, a lot of them do, because we look up in the night sky and we see them there, and there's certainly a lot. It's projected at about 10% of our stars in the Milky Way are similar to our sun. Scientists have not found an exact replica of our sun. There's certainly others that are very close. And as scientists become more familiar with the life cycle of different stars, our star, it seems to be in the middle of its life cycle, which is a very, very stable part of the life cycle of a sun, where it's staying about the same size and same intensity. And in fact, it should stay like this for a few billion years. And that's awesome, because I think life was intended to be on this planet for a long time, and things have gone awry, and so we hopefully won't be in our current condition for very long. but I believe that our universe and our planet and our energy source was all set up to be here for a long time. And we have evidence of that because of the long life cycle and the stability of our sun that we have. So we have a sun that's producing the right color, it's very stable, and it will burn for billions of years with hardly changing its size or its intensity. Eventually it will grow very big and engulf a lot of the planets that are nearby. We don't have to worry about that for a long, long, long time. So, and what's amazing about the sun is how it interacts with the Earth's atmosphere. So it turns out that our atmosphere, and in this graph right here, it shows it quite nicely, it blocks the gamma, X-ray, and much of the UV that is coming from the sun, and there is a window in our atmosphere that matches the visible spectrum, and it allows the visible light and a little bit of UV light to come through. Some infrared comes through, and a lot of the radio waves will come through as well. So once again, another coincidence that all the mixture of the atmospheric gases, the nitrogen, the oxygen, the ozone, carbon dioxide, they allow a window right through in the visible spectrum. And you can say, yeah, isn't that the way it's supposed to be? But we should call attention to that. That's pretty amazing. The sun is producing visible light, and we have a window right in the visible part of the spectrum to allow that light through. Another amazing coincidence that just happened in our solar system here. So the number of coincidences is just amazing. That's why we have to do these and talk about these things. So, and so we're going to continue to look at that. So that's really the amazing thing, is how a lot of the dangerous radiation that's very damaging to our cells is gone. Now we'd say, oh, the light, yeah, it's still dangerous to be out there, but it's not nearly as dangerous as it could be if there was a lot more radiation coming through. And I'll share a really clear example of the damage it can do a little later. We've got to learn a few other things. So the molecules that are involved in absorbing that are oxygen, ozone, water, carbon dioxide, and these are all finely tuned to give us that window right in the visible spectrum, and actually to absorb some of the infrared, because that's what bounces off the Earth, and by trapping that, we get the greenhouse effect. So all those molecules that we see there are finely tuned, as we've been talking about, to give us not only the chemical properties, but also, I call this optical properties or spectroscopic properties to allow us to absorb. So if you're designing a planet, you got to think about the optical properties, the chemical properties, and the health properties, toxicity. There's so many things you got to think about. So I just want to highlight again that oxygen is terrible at absorbing light, but there's so much of it in the path length, it's enough to absorb the dangerous radiation coming from the sun in the gamma and in the X-ray and some of the UV spectrum. Okay, so if its E is not very big, but the concentration is good and the path length is good too, and that makes up for the poor absorption quality. So those are things that scientists and spectroscopists, this is one of my favorite areas of science, is looking at how light and matter interact. And I'm just giving you a short version of it today. So let's do another little thought experiment here, just since we're talking about light and how it gets absorbed. We know that we're supposed to get some UV light, and it's important for the manufacturing of vitamin D in your skin, and there's a little chemistry, some molecules there to show on the slides there how cholesterol, a form of cholesterol in your body, is converted into vitamin D that your body needs for a lot of biological processes there. So that's important to have UV light exposure. So you need to have a certain amount of exposure every day. It doesn't have to be a whole lot to get your vitamin D requirement. So one of the questions I have, since I live in Michigan and next to Lake Michigan, we have a ton of clouds that come over us every day, especially in the wintertime. And it's just hard to get outside. It's so cold and it's cloudy. Can I go and just sit by a window and try to soak in the UV light that I need in order to get vitamin D? And one of the things that I'm going to just introduce here, and I'll go in a little more detail, there's different parts of the UV spectrum. And it turns out, I think actually I'll go back a slide or two here, that, yes, I did say it in my little chemical reaction here, that we need UVB light. It's a little bit further away from the visible spectrum, and I just so happen to have a lamp here and maybe Carter, I'll use you again. Come on up, Carter. So I have a lamp here that has 2 different types of UV bulbs in there. One, when we press it, will give us UVA light. That's near the visible spectrum. And then UVB light, I can press a button and we can get that light as well. And so why don't you go ahead and turn on the UVA light. Now, in order to see it, your eye cannot see it. Yep, press the white button there. We're going to hold her down. It takes a little bit. There we go. Now, in order to see this light, Carter's going to shine it on this piece of paper here. Just don't block the cameras. And see if we can get a little bit closer. How about like that? Go ahead and you hold it right there. Okay. Can you guys see the blue light? Okay, so it's called fluorescence. The UV light is stimulating some some molecules in there to create a blue light that we can see. Now, if something blocks it, right, it'll create a shadow. Let's see if my hand can block it. Oh, it's like going right through my hand here. There we go. So if something's blocking it, it will go, because you need to pull it back just a little bit so we can see the blue, and I'm going to be able. Now, I have this glass right here. Let's see what UVA light does. It's glass, right? It's going right through it. We're not seeing anything in particular. Okay, so this is like glass that's in your window. So let's go ahead and turn that off, hit the red button, and we're going to turn on the UVB light. Okay, go and shine it on the paper. It too will make it blue on here. So we want to tilt it down like that, okay, so that I can get some glass in there. Now let's see if the glass does anything to this. Do you guys see that? It's a nice blue light, and it's blocked. So glass actually, you think, is transparent. It's only transparent to your visible wavelengths, to what your eye works, but it blocks the UV light. Okay, so that's good. Thank you, Carter. Great job. And we'll set that right there. Okay, so you can go ahead and sit back down. We'll have you back up in a little bit. So the UV light actually blocks, or the glass blocks UVA light, and it does allow the UVB to come through, or does not allow. I got it backwards. The UVA comes through, and you need that to get tan, so maybe you can get a tan, although it's hard to do in the winter in Michigan. But it blocks the UVB light that you need for vitamin D. So what do you got to do? You got to get outside. And the poor cat looking out the window knows he needs some UV light. So, of course, best time, get out for a few minutes, try to get some arm and face exposure, which is terribly difficult in the wintertime unless you're trying to acclimate yourself to the cold. By wearing nothing but shorts outside, which I tried this last winter. Okay, and just for fun. So you need to get it, and it's kind of hard to do, but we really need that vitamin D. I think doctors would probably recommend, if you can't do that, you can try to supplement with vitamins and other things in your food. You could try tanning beds just for a little bit of time. I don't know if you can see the caption on my tanning bed. There it says tanning beds, and in very small letters it says sometimes you need to get cancer in a hurry. So you need to be careful, okay? See, the message is the same every time. Too little, not good, it's bad. Too much, it's bad too. There's the right amount that you need, and this is what I learned day in and day out from my work as a chemist. You got to put in the right amount. So you just need a little bit of UV light, and that can really help make up the difference. So I see an amazing fit between the light that we have from the sun, between the window in our atmosphere, and that light that comes through is very important for the chemical reactions that our body needs, like for vitamin D. And so there's the window. And then obviously for photosynthesis and how our eyes work for detecting things, and just an amazing fitness between what we have in our universe. And you can say, hey, that's another set of coincidences. Hey, life wouldn't take off without it. Well, maybe. But I just see coincidence after coincidence after coincidence. All right, so that's the first part of my talk here. The second part, I want to talk about how water is trapped. And we're going to continue to build on these ideas that we've talked about. Because, you'd say, well, of course Earth has water. And look, we have all of that. What do you mean? Why does it have to be trapped? Well, if you look at our neighbors, they don't have any water. Mars, dry. Venus, dry. Now, Venus has lots of gases on it, and Mars does not, but both of them are very dry. There's no water or very little to speak of. So they either had it and lost it, or maybe they never had it. So I think a lot of scientists believe they had it at their creation, and then it's been lost. Well, how did they lose that? And that's the subject of much scientific research. Now, when we talk about the sun, I was only talking about the part that you could see, or the electromagnetic spectrum. The sun is actually producing not only light, it is sending forth a bunch of particles. And it's like almost like a little machine gun, or a huge machine gun that's shooting out a bunch of particles. And that's called the solar wind. And these particles can do some pretty intense damage to planets and to atmospheres, and can blow off the atmospheres of planets if they're close enough. So all of these dangerous things that are coming from the sun can have quite an effect on living organisms. In fact, a study was done recently where twin astronauts were trained, and they sent one of them up for 340 days, Scott Kelly, and they kept his brother Mark here on Earth. And while Scott was up in space for those 340 days for nearly a year, they did a bunch of biological and biochemical testing, so they knew and of course you always have the twin control here on Earth. When Scott came back, his DNA was actually different. And I'm just going to read what I found as a report that just happened here. The report came out in March. About 93% of the changes were temporary with Kelly's genetic profile returning to the normal comparatively quickly. So when he came back, a lot of it changed and reverted to a normal genetic profile. In the case of the telomeres, the lengthening, this is the end of DNA, I believe, it vanished within 48 hours. But about 7% of the changes have remained in the 2 years since he returned to the Earth. Those involve genes related to Kelly's immune system, DNA repair, bone formation networks, hypoxia, and hypercapnia, the study says. That's a March 15th report that I found. And so when you're out in space and you're not protected in the way that you are here on Earth, what happen? You start to change genetically. And not always for the good. I mean, look, he's bald. No, I think both of them were bald already. Man, it's happening to me. I'm glad the camera doesn't shine from the back. All right. So, no, I mean, seriously, he started to change genetically being out in space. When you're not protected in the comfy confines of Earth here, the damaging radiation, both the solar wind and the electromagnetic light there that we get, start to break your bonds and change you. And you start to deteriorate, and you're at greater risk for cancer and other things. This is the problem with space travel. You'd say, oh, it sounds like it's hard to get to Mars. How do you keep your astronauts alive? How do you keep them protected? That's actually one of the greatest dangers. Yes, we want to have food and water all the way and be able to go there and come back, but traveling in space is how do you keep you alive like we can here on Earth? So there's a pretty amazing answer to one of the reasons why we're safe here on Earth. And so we're going to watch a video here, the first video this morning, showing NASA scientists talking about their study of the Martian atmosphere and why it does not have the atmosphere that it may had at one time, and compare it to Earth's atmosphere. So let's go ahead and roll the first video from NASA here.
Answer to the question, what happened to the Mars atmosphere? I'll quote Bob Dylan. The answer, my friend, is blowing in the wind.
Mars has something in common with the Earth and the other planets, and that, of course, is the influence of the sun. As you see in both of these graphics, all of the planets, Mars and Earth and the others included, are impinged upon by this flow of charged particles from the sun that we call the solar wind. These charged particles stream out from the sun at about 1 million miles an hour, and they impact all of the planets in our solar system. Now, the Earth and Mars have something that is very different, however. As you see on the right panel of this graphic, the Earth has a strong global magnetic field, and that magnetic field largely shields its atmosphere from the direct impact of the solar wind. On the left, on the other hand, Mars has no such global magnetic field, and its upper atmosphere lies completely exposed to the solar wind. As a result, the solar wind can interact with that upper atmosphere and strip portions of it away into space.
We are looking at the solar wind hits the Martian atmosphere, and it also carries a magnetic field with it. The moving magnetic field will generate an electric field in the upward direction in this video, and this will cause the planetary ions to move and escape from Mars.
Most of the stripping by the solar wind at Mars was thought to have taken place very early in the history of the solar system when the sun was much more active, when the solar wind was more intense. So today the rate of loss at Mars is low. Today's planet is a cold, dry, desert-like environment. The atmosphere is thin. It's not capable of sustaining liquid water at the surface today. It would either freeze or evaporate very quickly. However, when we look at ancient Mars, we see a different type of surface, one that had valleys that looked like they were carved by water, lakes that were standing for long periods of time. We see an environment that was much more able to support liquid water.
The NASA Mars exploration program has been focused on finding water. Water is the prime ingredient needed for life. It is a major factor in the climate and shaping geology, and it is a critical resource for future human exploration.
Can the same kinds of things happen to Earth now or in the future? And the answer is mostly yes. Earth is losing atmospheric particles. But as Jasper said, Earth has a big global magnetic field that shields the atmosphere from the solar wind. So some methods, some pathways that particles can take to escape the atmosphere of Earth are basically choked off compared to Mars.
Which we're losing any particles from the Earth's atmosphere is so slow, it would take tens or hundreds of millions of years to have any kind of impact. So amazing. We have this magnetic field. And tomorrow I'm going to talk more about how that magnetic field gets created and the amazing coincidences that are there to help generate that. So just for now, we have a magnetic field. And that is blocking that solar wind. That is amazing. So without the magnetic field, which not every planet has, right? Mars doesn't have it. So some planets have it and some won't. And there needs to be some special circumstances there in order for there to be a magnetic field. Earth has it, and we have a really strong magnetic field to provide a protective shield so we are not getting the solar radiation and the solar wind. Mainly it's blocking the solar wind. And those particles are just going and deflected around the Earth. Amazing. That's awesome. Now, there is something else that I just found out that scientists now have to think about when it comes to designing a planet that I never knew about, and it has to do with an electric field. So it turns out we need to think about how electric fields play into a planet. So our second video, our last video here today, is this planetary electric field. So NASA recently came out with a study that they did on electric fields on planets. Let's watch this next video.
I'm Gwyn Collinson from NASA's Goddard Space Flight Center, and I'm here to tell you today about the electric wind of Venus. So Venus is cool. Venus is awesome. Venus is, in many ways, one of the most Earth-like planets that we know of. One of the key ways that it's different is that it's very, very dry. With temperatures on the surface of 460 degrees centigrade, whatever that is in Fahrenheit, you would never expect there to be liquid oceans on the surface. That kind of temperature only boils off that water into steam, but the atmosphere of Venus is still incredibly dry. So where did the steam go? So to talk about how we remove something from a planet, we're going to have to talk about two forces of nature. Firstly, the force of gravity. Gravity is the thing which is holding you down to the planet, but if you think about it, it's also what is holding the atmosphere down onto the planet as well. If I want to remove some of the oxygen from the planet, we have to overcome that gravity. So to do that, I want to talk about the electric force. It's the thing which your device is using right now to pump electricity around its wires, right? It's pushing the electrons around the circuits. And what we think can happen is that the electric force can help push on the ions and in the upper parts of the atmosphere, push them off and up into space. So just as every planet has a gravity field, we think that every planet has a weak electric field. So we went looking for Venus's electric field, and boy oh boy did we find it. It turns out that Venus's electric field is at least 5 to 10 times stronger than at Earth. It's a monster of a force. It can rip heavy things like oxygen straight out of the upper atmosphere and send them kicking and screaming off into space. So this really changes the way we have to think about planets, because it turns out that planets can lose heavy things like oxygen to space entirely through electrical forces in their ionospheres. This is something that's really important if we want to go looking for exoplanets, for habitable planets around other stars. It is no good having conditions perfect for an ocean and an atmosphere that you might want to breathe if some invisible force is going to come along and rip it all off into space. Only understanding how atmospheres evolve can we try and understand how we got here.
So now there's another factor that scientists and planet designers need to think about, an electric field. And we don't have a very strong one. So that's amazing. We have a magnetic field, but we don't have much of an electric field. So it's not always what you have, it's what you don't have as well that's important in the design of a planet. So once again, that electric field is so strong, it can split water, it can kick off those molecules that make water, and then it will eventually go away. So we don't have that. So amazing things that are going there. So as it said, you know, gravity plays, we talked about this yesterday, plays an important role. It's selecting and keeping gases that are important on our planet. So I want to talk about this again. We're going to just relive some of our experiments here, maybe talk about some different gases in balloons. And I might need some helpers to come up on stage. And Carter, Christiana, you want to come up? And I think my wife was going to try this time to come up. And so when it comes to gases, you can have them with different densities. And we know if you have hydrogen or helium and steam, these are very light. They want to float up and leave the planet. And if we have really heavy gases like carbon dioxide, argon, ozone, and what's this other gas? Sulfur hexafluoride. These things are very dense. Okay, now in the back, let's see. Can you get Christiana or Carter? Yeah, get the white balloon. And this balloon here, why don't you go ahead, maybe you can throw it out to the audience here. This balloon, just come out here right to the front so they can see you throw the balloon. And do you think that has helium in it? You guys are going to have to get up. Does that have helium in it? No, that has something, man, it's bouncing. You guys feel free to get up and throw that balloon around if you'd like. So let's see, we have another balloon that has that. It's that balloon right there. And why don't you give that to your mother? Okay. And then, Carter, you want to take that one? Christiana, you want to do that one? Okay. Well, Carter has, what do you have in that balloon? I want you to just hold it up on your hand. Yeah, there you go. What do you think's in there, Carter?
Helium.
Yeah. So that's got helium in it. And so we're going to see the effect of these gases, and you're going to come over here to this microphone. And Carter's going to breathe in this gas. He's been taught some safety methods that after he gets done inhaling this, he's going to take a safety breath, inhale, and breathe out. So go ahead and say your name into the microphone up here.
My name is Carter.
Okay, why don't you go ahead and get some helium. Oh, you're doing great. Good job. All right, talking to the microphone.
My name is Carter.
Oh, you're so cute. Okay, keep talking here.
A, B, C, D.
Okay, now take a safety breath, and let's see if we can get that out of your lungs. Okay, talk, and this is how we check.
My name is Carter.
All right, you're back to normal. Do you want to try it? You want to try the heavy gas. This one's the light one. Let's have Mama try the heavy gas first. So I'll hold on to that. You walk up to the microphone. State your name.
Hello, my name is Susie.
All right. So this is what she does when I'm not around to help get some of that extra oomph in her commands to the kids.
Hello, my name is Susie. Welcome to camp meeting.
Christiana, which one do you want to try? Helium or the heavy gas? The heavy gas is sulfur hexafluoride. Oh yeah, we got to see if you're safe. Okay, come talk in the microphone.
Hello, I think I'm normal again.
All right. Christiana, which one do you want to try? The light one? Okay. So help get it off. All right, this is what we do for fun at our house. Seriously, I have tanks of these things. Now, we don't do it too much, but we do it once in a while. And go ahead and give that to Christiana and see if she can get some. Well, first of all, you come up here, Christiana.
We didn't pour it into her mouth.
Oh, that's the light one. You can't pour it. Yeah, it is. Yeah, it is. All right.
My name is Christiana.
Okay. You going to try this here? Just go. We did this at home. Hopefully it comes. Sometimes it doesn't open. There you go. There you go. What do you think? Come talk to the microphone.
Hello, my name is Christiana.
Oh, you're so cute. All right, I think that's enough for now. Oh yeah, do your safety breath. Thank you. See, they remember.
Can I try that little one?
Oh, you do it real quick. Go ahead. Yeah. So we put these back. Sulfur hexafluoride. I think it's the last one on my list over there, if you can see. Oh, yeah, you sound. Go talk in the microphone. Make sure you're normal.
My name is Christiana.
Okay. All right, here comes Carter.
Hello.
That's a little deep. You're fine. Okay, you're going to do some more? Okay, back into the microphone.
I got some more.
Yep. Yeah. Okay, take a safety breath. Because it's heavy, it will stay in your lungs, and we don't want that to happen. Okay? Thanks, you guys.
I think I'm back to normal now.
Okay. I want you two to stay up here, and we're going to talk about... So that's very important. Well, we would sound different. Thank you, guys. Thank you. Yeah, go ahead and set that back. All right. That's fine. All right. So these gases are very heavy. They want to sink down. They change your voice. It's awesome. And so look at ozone. So once again, that heavy one is sulfur hexafluoride. It's very safe. The reason why it's even available, it's so heavy, it quickly displaces oxygen, which is why you want to get out of your lungs after just a short amount of time. But they use it to fill up rooms if they think there's an explosive device in a room. You can flood it with this gas. It'll get the oxygen out. It'll lower the detonation risk. You can go in, defuse a bomb with much greater safety. So that's why it's available. And then you can do fun things like change your voice. Now, ozone is a very heavy gas. So we're gonna do some experiments with ozone in just a second. But let's understand a little bit about our atmosphere. And as you go up in atmosphere and altitude, what happens to the temperature? Right, it gets cold. You can just look outside the window and look at Mount Rainier and go, man, it's cold up there. And that's true, it does, but it doesn't just get colder and colder and colder and colder. It does get colder to a point in the troposphere, and then you get to the stratosphere, it actually starts to warm up again. And then you get to the mesosphere and it cools down. You get to the thermosphere and it really heats up. So it doesn't have to be cold as you go up. It does get cold where we are as you go up in the troposphere. So the troposphere gets really cold. In fact, it gets to about minus 50 or minus 60 degrees. That's enough at the top there to really freeze out water. But other gases like ozone, oxygen, nitrogen, and helium and hydrogen, all of these things go right through that. Minus 50 degrees Celsius to gases like oxygen and nitrogen means nothing. It's still nice and toasty warm for them. They go right on through. They do not feel any of that temperature change. They stay as gases. But water, on the other hand, freezes out. And that right there alone traps most of the water. So that's very important because water becomes a solid at that temperature. It's a lot more dense at that point. It can sink down, and we are trapping out water. You'd say, there you go, that's enough. But the story is more complicated than that. Okay, notice the location of ozone. Ozone is in the stratosphere. That is above the troposphere. Now recall, ozone is a very heavy gas. Why is it not down at our level? A little bit is at our level because it gets created here, but most of the ozone that is protecting us is in the stratosphere up where heavy gases should not be. But there it is. How is that? We've got to learn a few things about ozone to understand that. How is ozone created? Ozone is created from oxygen. When lightning or electrical energy or UV light passes through oxygen, it will create ozone. It splits oxygen up, one of the atoms combines with another O2, and it creates ozone. I have an instrument here from this company called A to Z Ozone, and it uses electricity to generate ozone. And I can turn this on, and there's a bunch of settings for as long your time and everything. Now ozone, why would anyone want to do this? Yes, you go ahead and put it in the water there. Okay, this is going to come on in just a second. All right? And you can see the bubbles forming in the water here, and this forms ozone, and it's fun to smell. How many people have smelled ozone before? Okay, would anyone like to smell ozone? Does anyone want to smell ozone? Why don't you can come up here, and Carter's going to bring you one of these flasks, and you can just come smell it. We put it in the water so you can come smell it. It won't hurt you too bad. No. So Carter, go ahead and grab that one. Okay? You go ahead and take that over to her, and then we can do another one here. Does anyone else want to come smell it? You can come over here, and Christiana is going to take one. We'll take this one over there. I put it in the water so that the gas is kind of being trapped a little bit. Okay? So go ahead and take that one over there. Yep, go over there. Now I've got two of these flasks that have blue food coloring in it. And I'm going to put ozone into one. This is going to illustrate one of the other properties here. See if you guys take a good whiff of ozone. I'm smelling it nice here. You can often smell it when you're around electrical equipment. Do we need some more? Oh, it went away, huh? Okay. So this is one of the properties of ozone that we need to know, is that it goes away pretty quickly. Okay. Did you guys smell it? Okay. Smell great? No. Yeah, it's a little bit like a chlorine smell. Thank you. That's actually a great analogy. We need some more in there? Yeah, it goes away. Okay, here we go. I'll put some more in yours. Yeah, it goes away quite quickly. It doesn't want to stay in the water. Whew, smell it nice and good there. Everybody getting a good whiff? Go ahead and take that over there. Okay, thank you. Now we want to see the effect of ozone on basically hydrocarbons, organic matter, things that are built out of the same kind of bonds that life is. And this ozone here is actually quite destructive. Whoop, okay, that's great. I think we've got our buddy that maybe want to smell. We can always do it afterwards if you're interested in it. So I'm just going to let that go. I think that's about it for this demonstration. You guys can go back and sit down. Thank you for your help. You guys are wonderful. Do you guys see any changes yet? I don't know if you can see anything yet. Anything seem to be happening with this one? Yeah, it's a little bit lighter. We're going to keep our eye on that. So there are air purifiers that will produce ozone. You can buy these things. Why would anyone want to have ozone? Does anybody know? It does get rid of odors. Yep. You know, and it's heavy enough it'll come down. Yeah, it'll help get them out of the air. It destroys them. What do you think? Oh, yeah, it's nice if you had one. You could put one in a hotel room if there was smoke or something in there. That's right. Now, actually, these are used down in the industrial level to purify water. It's another way besides using chlorine bleach or chlorine products to get rid of things. Can you guys tell now what's happening? Yep, so there's the original control. Do you see any color? No, there's very little, if any, there. Maybe just a little bit. Okay, the ozone is destroying the blue food coloring. It's a very destructive molecule. Okay, we got to know a little bit more about UV light too. So it's a destructive. It's destructive. It's heavy, but it goes away very quickly. It's a very reactive molecule. It is definitely a disinfectant. Now, I think I have that on another slide here. So we're going to learn one more thing about UV light. So UV light, we talked about A and B and C. Well, A and B. There is a C. There's just different parts in the UV spectrum that we should know about. A is basically what black lights and other UV lights give off. I have one that gives off UVB. Now, one of the properties of UV light actually is, if you look under the UVC category there, the row over to the right, UV light, it can actually be germicidal. That's because it actually starts to split water. UV light has the ability to go in, and there's enough energy there, it'll break the bonds between oxygen and hydrogen, and when you have a lot of it there, it will produce oxygen gas and hydrogen gas. So UV light is especially dangerous to water, and it will split it, and it can go away. Now, one of the important things about ozone that we want to learn about is that it is created from oxygen, but it has a slightly different, what's called an absorption spectrum, that's different from oxygen. And in this graph, I love this graph, you may be new at reading this graph, But what it shows on the x-axis, the horizontal part, is the different wavelengths of light that these two molecules absorb. They don't do them very well, but when you get lots of them, it makes up for the difference. Oxygen absorbs light from about 180 nanometers and lower, and then ozone takes over and can absorb more of the UV spectrum. And so where oxygen loses out, ozone makes up the difference. So ozone is created by UV light hitting and the radiation in space coming from the sun hitting oxygen. It creates ozone, and that ozone and oxygen work together to block more UV light, but allowing just the right amount to come through. So it's very important that water does not, especially in our upper atmosphere, get struck by the ozone. Get struck by the UV light. And so if it did, it would split, and the hydrogen part would leave, and we'd be left with all of these oxygen atoms, which would be great for breathing, but it would be terrible for having water. It's called the photolytic splitting of water using UV light. Okay, so that's nice. Now, ozone is very nice from a spectroscopic perspective because it blocks the UV light. And it blocks it in the right spots. Okay? So how does that happen? Well, so what I have here, the little blue part around the sun is the troposphere, and that's where water goes up, it freezes out, and then it comes back down. Now, the ozone layer is right above that, acting as an umbrella and blocking the UV light so it does not split water. So we have the protection and the creation of ozone taking place at the correct level up in the stratosphere from the UV light hitting the oxygen atoms. Okay? So how does the ozone end up there? Well, that's where it's created. It's created by oxygen and UV light, and it's created in the right place. If it was any lower, we'd have more UV light hitting the water as it's freezing out, splitting it, and letting the water go. So we have a protective umbrella ozone layer up there. Well, what keeps it from coming so far down? I think I got my stuff a little out of order here, but we did the control here. We put ozone in. It destroyed the blue food coloring because it's a very destructive, very reactive molecule, and the reason why it's only up there, mainly, and gets trapped up there, is it's very reactive. And it is a lot like bleach. So this is a Clorox bleach, and I made my own ozone bleach there. And so we have to be careful. I mean, would you go around and breathe bleach? Sure, you would do a quick sniff, but you would not want to sit there and breathe it for a long time. You don't want to do that with ozone as well. It will go in and destroy your mucus lining, making you more susceptible to getting sick and things. So having a little bit in the air is fine, it will go away. I actually worked for a company that made an instrument like this, and they put it in a squirt bottle, and you could spray a surface, disinfect it just like you would bleach, but the ozone disintegrates and goes away, and so you have no chemical residue. And it sold terribly. Nobody liked it because they couldn't smell it working. Well, you could initially, but then we like that bleach smell that lingers on. So it's a very powerful disinfectant, just like bleach. This is why cities will often use it to purify water. And it's nice because then the ozone goes and you don't have the chlorine residue. But it's very unstable. What I have here is a table of how long ozone lasts, depending on temperature and whether it's in water or not. But the point is, ozone just doesn't last very long. So what happens is it gets created in the upper atmosphere, and as it's heavy and it sinks down, it reacts with other oxygen, nitrogen, and other molecules and goes away. So I call it a kinetic trap. As it moves, that's what kinetic means, it breaks apart and gets trapped. And all of that happens in the right spot so they can block the UV light before it hits water and splits water apart. So the ozone layer is safely above us, so we're not breathing it, although larger cities will often have ozone alerts because of the electrical equipment that's there in the summer with air conditioning and those kind of things. So what if the ozone layer was lower? Well, if it was lower, then UV light from the sun would be able to strike the water, split it, and we would lose all the water, at least part of it, that's hydrogen, out into space. But that doesn't happen. So we would lose all of those small molecules. So some days you can see the cold trap in action where you see these mushroomy, billowy clouds that are often hitting the upper troposphere, freezing out, and the water's coming back down. It's like there's a cap, and it's amazing. So between the cold and the UV blocking ozone layer, we have it. So let's review how all this works very quickly, and then we're going to get the nitrogen. Water freezes out in the troposphere, which just so happens to be colder going up. We saw that not every layer has to do that. And it happens to get cold enough to work efficiently. And we have oxygen. It stays as a gas. It goes through that cold troposphere, so it doesn't freeze out like water. So it makes it through the cold trap. And once it's above there, it is able to generate ozone from the UV light, creating a better broad spectrum blockage of the UV light so that it will not split water. So you get that further protection in the right area. So all of that just happens to be in the correct location. And don't forget that we have a magnetic field that is strong enough to block the solar wind, and we do not have an electric field that could split water and shoot it off the planet. And that's how our water's trapped. And we just thought it just had to be cold. No, it's all of these things working together to trap the water.